Well, welcome to Unit 3, the unit where we will talk more about light and color, and we will also dip into a little bit of polarization. So, Isaac Newton, the scientist that we've studied and learned about Newton's laws of motion, actually did some experiments to help us understand light and color a little bit. From his experiments, he concluded that sunlight consists of a mixture of 7 colors. And we know those colors. Those are the colors of our rainbow. And all the colors that we see are various combinations of these colors. So typically, the way we get the rainbow is you have sunlight coming in, approaching a raindrop. And as it gets into the raindrop, we have a change in the material, and it's going to interact with that matter. And it slows down inside the raindrop, which is made of water. And so you have the spreading or the bending of the waves as it passes from the air to the water. Now, inside the raindrop, we have the different frequencies, and of course, in the sunlight itself, different frequencies and wavelengths of light. And so, as they get refracted, the different frequencies and wavelength bend by different amounts, and so we get that initial spreading. On the other side of the raindrop, when the rays hit that other side, they undergo total internal reflection. They come back, they spread a little more as they reach the second refraction or the second bending. So the observer will see what we know to be the colors of the rainbow. So how do we use light to help us actually see? We have different kinds of lenses. And as the light rays pass through these different lenses, there's a difference in what happens to the rays. In the first lens, we see the rays are spreading out. That's called a diverging lens. The second lens, we see the rays coming together or converging to meet at the point. That is called converging lens. Now, when any light ray passes through the lens, just like it is for the raindrop, we will have refraction occurring. And this refraction is going to dictate how the rays actually meet. So for example, with our convex lens, we have a certain point at the center of the lens that we call the principal axis. And rays that pass through the principal axis pretty much pass through there unrefracted. Well, there's refraction, but the bending actually makes it go along a straight line. And then you have the rays that's going to actually come to a certain point at the top, and because of refraction, the waves travel all the way down, and you can follow the ray along path too, and we see that also is refracted down. And so what you have happening there is the rays all meeting at a certain point. Now these rays, we're looking at these 3 rays that came off from the tip of this blue arrow. And so if you look at the rays as they meet, we know that's where the tip of the blue arrow is. The point where they meet, that's where the image is formed. So we have an object, and this is its image. The image is the same size. The image is upside down. We call that upside down inverted. So we see the image is inverted. And because this image is formed from the rays actually meeting, we call that a real image. When we talk about rays forming an image, but it's from where the rays appear to meet, we call that a virtual image. So we have the use of lenses in different forms to form images. We talked about our diverging lens. Another name for it is concave lens because it has this concave part to it. And its uses in vision correction. Of course, it's used in association with other lenses. And then we have our convex lens, which are our converging lens. It's the most commonly used lens for magnifiers, cameras, eyeglasses, telescopes, so on. Now, the human eye actually has a lens. That lens is a convex lens that has a muscular controlled curvature that can change its focus. So if we're looking at something far away, the muscles will adjust our eyes or the lens in our eyes accordingly to make that light from a faraway object bend or converge and meet at a sweet spot, which we call the retina in the eye. So we have the light rays coming in. It passes through that hole in our eye called the pupil. And right behind that is where we have the lens, and the lens are attached with these muscles here. The light coming through converges, and we expect those light to see the one from the top goes down, the one from the bottom goes up. We expect the light to form an image on the retina, which has all these blood cells and sensory cells that can detect the stimulation from the light. That image is sent via the optic nerve. Our brain interprets it, flips it up, right side up, and we are able to detect the image. So what happens when we have defects in our eyes? When the muscles in our eyes cannot really make that image form on the retina. So in the case with normal vision here, we see from a faraway object, the light rays are coming from a faraway point. The lens is a little bit skinnier. When it's coming from a near object, the lens gets fat. Now, if our muscles are unable to correct for that, we have to correct for our nearsightedness and farsightedness. So for nearsightedness, we can see things very well when it's close up, but not very easily when it's far away. And farsightedness is when we can see things when they are far away, but not very well when they are close up. So nearsightedness, the image form in front of the retina, and farsightedness, where the image form behind the retina. And so we will use lenses and contacts to help move those images onto the retina. Now let's talk about another characteristic of light, which we talked about as making the assumption that light is a transverse wave. And we actually have an experiment that shows us that light behaves like a wave. And this was done by Thomas Young, and he provided evidence that we have for the wave model of light. In his experiment he performed, which is called the Young's double slit experiment, he actually used a system where he had single slit, light rays coming in, and as we learned earlier, when light goes around a narrow slit, the light undergoes diffraction. I was at the spreading out of the wave. Then he took that diffracted light and he sent it through two slits. So the light got diffracted through each of these. And then he saw regions of light and dark bands, similar to what we expect with waves when they interfere constructively and destructively. And when he was able to observe that on the screen, he was able to show then that light does have a wave-like characteristic in that it undergoes construction or constructive interference and destructive interference. All right, so let us talk a little bit about here some of the characteristics of this wave-like behavior. Now, we said earlier that electromagnetic waves are transverse waves, and that means that the direction of travel is perpendicular to the direction of motion of the wave. So we have light ray coming in all different directions. We call that unpolarized light. But if we take light through polarizing materials, we can transmit the light vibrating only in one direction. And that's why it's said to be polarized or plane polarized. So, oopsie, let me close this and go back here. This is going to tell us about, it's a video that's going to tell us about how we actually get these polarized lenses to work. Let's see if it pulls up.
So if you are a sunglasses collector like me, or perhaps you're just looking to buy a new pair of sunglasses, you probably noticed a little P symbol in the top right corner of your sunglasses, or saw the word polarized and wondered, what's the difference between polarized versus non-polarized sunglasses? And that's an excellent question. So that's what we're talking about today. Let's take a look. Hey, what's up? This is Dr. Allen here from the Dr. Eye Health Show, helping you learn all about the eyes, vision, and finding the best vision products. And today we're talking all about polarized versus non-polarized sunglasses. Now, myself, I'm a huge sunglasses collector and fan, and I'll tell you something, polarization makes a huge difference when it comes to sunglasses. If you've never heard of polarization before, or just wondered what in the world they're talking about when they mean polarized, we're talking about how sunlight or light coming from any external source comes down and hits an object and then reflects off of it. When that light comes down from something like the sun, it is coming in every single direction. It's coming from a horizontal direction, an up and down vertical direction, every possible angle that you can possibly have. So when light comes and crashes into an object, specifically an object with a flat horizontal surface, such as the road, a car windshield, maybe a large body of water, such as a lake, a river, or an ocean, then the light that radiates from those objects doesn't scatter in all directions. It's going to bounce off in a flat horizontal way. And we call that polarized light. And if you have some sort of a technology, such as a polarized filter that selectively neutralizes that exact horizontal light, then you can eliminate it and you won't see that whole reflection. It's pretty wicked. And just to help show you guys what polarization really can do for your vision and your visual experience through a pair of sunglasses, I grabbed a couple of my sunglasses, ones with polarization, some without polarization, and I took them out to the road and onto the water so I could show you what it really looks like. So hopefully with those little video clips there, you're able to see the difference of with and without that polarized filter. And one thing that's kind of cool is that polarized filters, they are oriented a certain direction to neutralize that horizontal reflecting light. But that means that you can rotate a polarized filter and change the amount of light passing through it. So for example, if you're wearing sunglasses and you tilt your head to the side, you are changing the orientation of that polarized filter. And then you can really see the big difference. So if you ever see me walking on the side of the road, you'll probably see me just being nerdy enough where I tilt my head side to side to side all the time. That's not just because I like to bob my head in different angles. It's because usually I'm wearing polarized sunglasses, and I just find it entertaining to watch the different reflections of light coming off of a surface. So maybe you're wondering, hey, do I really need polarized sunglasses? I don't think anybody absolutely needs polarized sunglasses, but if you are somebody who's very light sensitive, or you're just very big into sunglasses and seeing your best, maybe you're somebody with migraines and you have difficulties with these bright reflections coming off of objects, then yes, I think polarized sunglasses are probably the best choice for you. If you're somebody who also likes to drive a lot because the roads can get wet, or you can see a lot of glare coming off of windshields and a wet road, for example, then yes, polarized sunglasses are going to also help you a ton because it's going to reduce all that extra glare. Now, one scenario where having polarized sunglasses is an absolute must, in my opinion, is if you are looking for the best sunglasses for fishing. And that is because when you're on a large body of water and you're fishing, you're looking down directly into that water. And it's usually at just the perfect angle to see a lot of reflections of the sky or something above you. And so if you have polarized filters on, you can eliminate that glare and see directly into the water. And you can even see fish and different weeds and rocks, everything. And to simulate that effect, I even filled a large bowl of water and put my watch in there just in case had an idea if you were maybe out on just a low, shallow river and you dropped your watch or something in it and you couldn't quite see where it was. Sunglasses with a polarized filter in them, if you rotate them the right way or just look in there, you can see my watch in this video really easily as compared to if you didn't have the polarized filter on there. You just see a huge reflection of the sky. So yes, if you are into fishing at all, even in just a little bit, you're going on a big fishing trip or something like that, definitely pick up a pair of polarized sunglasses. Yes, polarized glasses are my personal favorite, and I pretty much prefer to wear them all the time. But there are some scenarios where you do not want them. Yes, if you're fishing, you want to have them. Yes, if you are somebody who's driving a lot, you're on the road, you see a lot of wet roads, you can see light bouncing off that flat horizontal surface of asphalt, maybe car windshields. Yes, polarized lenses, polarized sunglasses are ideal for those situations. However, if you are somebody such as an airline pilot, if you're in the Air Force, maybe you are in the military, or maybe you drive a ship or something and you're looking at a lot of electronic dials, then no, a polarized pair of sunglasses is probably not ideal for you, at least when you're using those electronic dials. And that's because if you are in something like a cockpit, your airline pilots, their dials in front of them in the cockpit are no longer just mechanical dials that go back and forth. They're usually made with computer screens. And something that a lot of people don't know is that computer screens have polarized filters in them. And that's exactly why if I hold up this polarized filter here for a camera and I rotate it just the right way, you can no longer see through it. That's pretty wicked, right? So I can kind of go non-polarized, polarized, non-polarized, polarized. And that's because the polarized filter of the camera filter here and the polarized filter in the computer screen are polarized against each other, and you just can't see through them at all. And that's why if you ever wear polarized sunglasses and you pull to like a gas station and you look at the electronic dial that tells you how much fuel you're pumping into your car, you might not be able to see it. And that's because the polarized filters in different kind of computers and electronic screens can negate each other and you can't really see it. Sometimes you can see this in car radios, sometimes on older phone screens. It kind of does depend on a few things. Now, a good question I've got from patients and viewers is there a difference of polarization from one company to the next in terms of different brands of sunglasses? And honestly, I don't know. I've looked into it and I'm not really sure if there's a difference in technology of one polarized filter versus another. Certainly there's a difference in quality of glass or plastic, of how your sunglasses are made or what type of brand made the filter for your camera polarized filter. But in terms of how the polarization is made, I don't think that makes a difference. But I do pass that off to you. If you know a little bit more about how polarized filters are made, and if there is really a difference of polarization effect of one company brand versus another, I want to know because I'm just nerdy like that. I like to know those things. But thankfully, polarization technology is available in sunglasses, and honestly, I think it's pretty cool. If you haven't tried them, recommend it. Hey, I hope you liked it.
All right. So what we perceive as glare is usually reflected horizontal light. Another fact we learned from the video, that polarized lens remove the glare by allowing only vertical lines to pass through, and hence it's polarized. So in this little image here, you can see we have the waves coming in all direction, and it's removing that horizontal glare, so we only get the wave in one direction, and that helps eliminate some of that glare that we will observe. So notice on polarization, we can have unpolarized light. We can pass it through different polarizing filters where it eliminates the horizontal components, and we can only have those vertically polarized light. If we take light that's unpolarized through a vertical filter, we'll only have the vertical filter light, because we would filtered away all of the horizontal light. And then if we pass that through a horizontal filter, then no light is able to get through, which is what we saw happen in the video. So unpolarized light is a mixture of randomly oriented fields. Polarized light are really electric fields oscillating in one direction. And two filters, passage depends on the alignment of the filters. And we can have cases where the filters are so aligned that there's no light passing through it. And in the case where we have reflection polarization, that comes from things like lakes and rivers and oceans that he talked about, where most of that reflected light is along the horizontal plane. And so we can take that a pair of polarized sunglasses that is going to take away some of those reflected horizontal fields and then reduce the glare for us. So that is the end of our color and our discussion on polarization. The next section will be on the particle theory of light.